For today's CGD seminar, we have the great pleasure to have David Crisp talking about carbon dioxide measured from space. And Dave, I think, was originally did his work at Princeton in the 1970s with people like Isaac Held and others, and has worked on Venus probes in the atmosphere for NASA. And maybe 20 years ago, came up with the idea of measuring carbon dioxide from space, which is a very challenging effort. And it's come to fruition with the launch of the OCO2 spacecraft, 2 launches actually, one that didn't work, and then another one 10 years ago or so that did get up in the atmosphere and has been producing great data for the past 10 years. And Dave is going to talk to us about the variety of uses that that data can be put to and how it relates to climate and policy. So with that.
So let me just make sure the mic's working. Everything looks good.
Does he use this one?
Yep, good enough. Okay.
Maybe you can turn that off.
Yeah, you want to turn that one off or we'll get some feedback. Okay. So let's see, I wrote this presentation primarily for my colleagues here at NCAR, not necessarily the ones that are here visiting for the Transcom workshop, in part because they know all of this stuff, right? So what I tried to go ahead and give a presentation that talked a little bit about what we're talking about when we're talking about top-down carbon fluxes. I'm going to start off by a quick overview of where we are and why we care about these things. Some of you know very, very well why we're studying things like carbon dioxide and methane emissions in our atmosphere. And it's because they're modifying our climate. We're doing a little inadvertent climate experiment on ourselves here. Human activities are now dumping about 40 billion tons of carbon dioxide into the atmosphere and a bunch of methane as well every year. These large inputs of carbon dioxide and methane have increased the mixing ratios of these 2 gases in our atmosphere by an astounding amount. We've increased the CO2 mixing ratio by over 50% since the beginning of the industrial age. We've increased the methane mixing ratio by 160%. Most of this has happened in a very short period of time during our lifetimes, which really ought to scare you to death. So we're modifying our planet in big ways in terms of its atmospheric composition, and that's having an impact on our climate. At this point, carbon dioxide and methane alone are contributing over 90% of the observed 1.1 degrees centigrade global warming. This has been talked about in the IPCC reports and so forth. So we know about all of this, and we know what the causes are. We know it's anthropogenic emissions. Why are we studying CO2? Well, and methane. Mainly because CO2 isn't being emitted only by anthropogenic activities. In fact, we're a pretty small player in this. Human activities are dumping, as I said, about 40 billion tons of carbon dioxide into the atmosphere every day. It's just a source. We don't pull very much of it out. But that's superimposed on a very active natural carbon cycle. And the natural carbon cycle is actually emitting about 20 times as much carbon dioxide into the atmosphere every year as anthropogenic activities, and then absorbing a comparable amount, along with about half of the emissions from anthropogenic activities. Okay, so it's basically cleaning up half our mess. And if you think something like 35, 40 ppm increase in carbon dioxide since the turn of the century is really bad news, think about twice that if we didn't have the natural carbon cycle sopping up half the mess we've been put into it. It's a really big question. But the issues here are, as we'll go through this, we'll find that we don't really understand this carbon cycle and haven't quantified it quite as well as we'd like. So, for example, you understand that plants perform photosynthesis that absorb carbon dioxide. They also have respiration, which re-emits that carbon dioxide back to space. We also know that the ocean, through just Henry's law, absorbs carbon dioxide through its surface. Then biological processes in the ocean take out carbon dioxide up, pick some of it, dump it into the mud in the bottom, and it's gone forever. So these things are going on, but but also there's ocean respiration. So a lot of that CO2 that's pulled into the ocean water as it's moving around by the currents that some of you are actually calculating, these bugs are respiring and they're producing more carbon dioxide. So sometimes the carbon dioxide that comes up is actually richer than the stuff we put down. Okay, so that's kind of the ocean. Now, so how do we know what we know about the carbon cycle, both our emissions and also the anthropogenic? the natural carbon cycle. It's because since the 1950s, we've been deploying a larger and larger number of ground-based sites that are making measurements of carbon dioxide. There's a little map over there. We have, of course, the Mauna Loa site. We have the South Pole site. But we've added more and more stations over time, or I should say our colleagues at NOAA have. And now we have basically pole-to-pole coverage with a number of stations, and they're making carbon dioxide measurements, usually in situ with flasks, or now with non-dispersive IR, or with cavity ring down systems, and they're showing us the carbon cycle. And what we're seeing is actually the seasonal cycle of the carbon cycle, with basically drawdown in the northern hemisphere, and then basically inhale and exhaling of carbon dioxide during the seasonal cycle. But as I've been talking, have you noticed how the whole curve's just been kind of moving up like that? That's the anthropogenic impact. We're simply a source. So over time, our carbon dioxide gets added to the atmosphere, and it mixes fairly uniformly across the atmosphere, and that's increasing the carbon dioxide abundance shown in the Keeling curve over there to the right over time. That's just mostly up. The up and down, that's the seasonal cycle, that's the natural carbon cycle. The going up, that's basically us. But once again, keep in mind that set of stations on the surface of the Earth. There are a couple hundred of them that are making measurements. So what is this teaching us? Well, this plus some information that we have from what we're actually doing, something called bottom-up inventories, and we'll talk about those in a little bit more in a minute, are cataloging the amount of carbon dioxide that's being emitted due to fossil fuel combustion. And that's that gray curve going up. And the gray hatched area around it is the uncertainty in that curve. You might notice that, first of all, that's a lot of carbon dioxide, and it's been increasing a lot since the 1960s. It used to only be about 10 tons of carbon dioxide. We've increased that by a factor of 4 as we've kind of marched through the series here. But notice that the error bars are kind of small, and why is that? Most of this comes from, this is burning fossil fuels. We actually tax fossil fuels when they're extracted, when they're transported, and when they're used. And so there are pretty good records on fossil fuels throughout most of the world. Notice, though, that the error bars have gotten a little bit bigger over the last few years. What's going on there? Now about 60% of the fossil fuel emissions are coming from the rapidly developing world. And they don't quite have the record-keeping capabilities and in order to track things as well as we've learned how to do in, say, the US or Europe or Japan or Australia or someplace, right? So once again, the error bars have gotten a little bigger on that curve. But the curve down on the bottom is a very different beast. That's actually land use change. So this is basically deforestation is the thing that we know about a lot, but it's also just transferring fields to forest and forest to fields everywhere, and a lot of agriculture going on. And as we do that, we also are emitting carbon dioxide in the atmosphere, much, much less than we do through fossil fuels. But once again, we're still emitting some, and that's going down slowly over time as basically our practices are improved. And hopefully, as we deforest the Earth, there's just not that much to chop down and burn anymore. And so what you would expect is we're making all these measurements from this series of a couple hundred atmospheric stations. So you would expect maybe if we're dumping in that much from fossil fuels and that much from land use change, that the actual rate of growth of carbon dioxide in the atmosphere every year, the buildup of carbon dioxide, would be something like the sum of those two. It's not. What the ground-based measurements and atmospheric and airborne measurements are telling us is that the rate of growth of CO2 is only about half of what it would be if all of the carbon dioxide we know we're dumping into the atmosphere stayed there, okay? And notice the error bars on that are really small. We can do a very good measurement of CO2 in the atmosphere, okay? But notice that there's a lot you can see about this. I could talk about that curve for ages. But notice, for example, there's a lot of variability in that curve of atmospheric growth rate. What's going on there? Well, sometimes we have big El Niños, and in big El Niños, like the ones we've had in 1998 and in 86, also in 2015, 2016, basically during those periods, we see that the land biosphere doesn't absorb as much carbon dioxide, okay? The ocean actually emits less, but the land biosphere doesn't absorb as much. And so that creates a larger fraction of what we put into the atmosphere stays in it during those years, okay? Other years, during La Niñas, also during volcanic eruptions and so forth, the Earth cools off a little bit, and all of the systems tend to absorb a little more carbon dioxide. But there are a bunch of other processes, most of them we don't understand, that are contributing to all of that variability that you're seeing. What's it going to do in the future? Any guesses? That's exactly what they would be. Because right now we don't understand the system and how it works well enough to understand how it might behave in the future as it responds to continuing human activity and climate change. We just don't know where it's going, okay? So, but we do have better and better bottom-up inventories. And bottom-up inventories, we'll learn more about those in a bit, are places where we actually go and add up all of the sources of carbon dioxide we know about, add up all of the sinks. And what we see is that basically 35.5 or 3 gigatons of carbon dioxide entered the atmosphere last year due to fossil fuel combustion, about 4.7 due to land use change. Some of that stayed in the atmosphere, about 47%, about 31% ended up in the land biosphere. We think that's a little bit uncertain. And then about 26% ended up in the ocean. Once again, that number is somewhat uncertain. We know what the total is. Where it goes between land and ocean is still a little bit less known. Methane's a similar but more complicated picture in some ways. Methane doesn't have a natural sink besides OH in the atmosphere and a little bit of uptake by the soil. So basically it's got a very kind of minor and fairly well understood but not understood sinks. We don't know the OH decomposition of methane in the atmosphere, something we sort of know about, but once again in detail we don't know about. But the main sources, agriculture and waste, fossil fuel, and wetlands, natural wetlands are the main sources of methane emissions. We're actually not the biggest player over here in terms of the anthropogenic emissions of methane. So natural wetlands are the largest natural source. It's over there about the middle green curve over there. And they've been changing a lot in recent times. But there's actually, methane has a stranger story than CO2. You might have noticed that nice Keeling curve just going up and to the right that I showed before for CO2. It's been pretty steady. We can track it back to a specific process. This is the methane growth rate over time, or the change in atmospheric concentration over time. It's doing really weird stuff. The little green bars I just put in there, we really don't know what's going on with methane. In the 80s and early 90s, it was increasing in the atmosphere really fast. Then it kind of just leveled off for about 10, 15 years just for the hell of it. And now it's starting to come up again, and it's actually accelerating in its rise over time. And some people, like John Warden, has been spending his life trying to understand what some of these processes are. We know that natural wetlands are really, really, just by the way, you can do isotopic analysis of the stuff that's coming in and out of the air. You can learn some things about it that way. You can learn things about it by making other types of bottom-up measurements. So we know something about it. But once again, there are large uncertainties. We don't know the extent to which natural wetlands and agriculture, if you together, we know they're producing probably the biggest effect you're seeing here. But we don't know, nobody can really put their finger on the values to any kind of level of accuracy or trace them back to specific processes. So most of it comes from natural wetlands and agriculture. The rest of it, but believe it or not, CO2 production and use, fracking, all of that stuff, it's probably not the major contributor here. How do we know that? Once again, the isotopic makeup of fossil methane is different than the isotopic makeup of methane that's been around and being moved through the system. So we can learn something about it from those kinds of measurements. So let's look at top-down and bottom-up methods. I'm going to introduce top-down methods. We've been talking primarily about measurements made in what we call bottom-up methods. So what are bottom-up methods? Bottom-up methods are what they use to compile inventories for things like, the EPA does this, for example, for their regulatory requirements, and also to report to the UNFCCC, okay? And what you do there is you basically take a certain activity factor, you multiply that by an emission factor. So you might have, I show a power plant here. That power plant might produce a certain number of petajoules per year. We know that's the activity of the power plant. We also know that how many tons of CO2 is generated for every petajoule of electricity we generate. We also know how many tons of CO2 are added to the atmosphere for every ton of coal that it burns. For example, if it burns coal. You can do this several different ways and get a pretty good estimate of the amount of CO2 you're adding to the atmosphere just from these bottom-up methods. If you have a forest or a field or some transplant between the two in your domain, once again, number of hectares of field that were converted to forest or vice versa is something that we refer to as the activity, and the number of tons of CO2 per hectare that are generated by each of those conversions is basically our emission factor. Now, as you might imagine, this emission factor over here for fossil fuels is known really, really well. A gallon of gasoline dumps 20 pounds of CO2 into the atmosphere, okay? What's an acre of grassland or forest dump into the atmosphere? Any guys, ideas? Your idea is as good as anybody else's. We know this for a few places on Earth. We use it everywhere. So the uncertainties in land use change from bottom-up inventories is much, much higher. Order 1 is what you saw on the curves I showed earlier, than it is for fossil fuels, okay? But it's a big world, and the big world's dumping 20 times as much CO2 into the atmosphere every year as human activities, and bringing that back in, we'd better understand it. So how do you do that? Well, you might want to use top-down methods. So in top-down methods, and by the way, you just do this for everything in your whole domain that you care about, the country you're in, or the region you're in, or the hemisphere you're in, you would just keep adding together all the pieces and parts that you know about. That's how you do a bottom-up inventory. Top-down budgets, we can't really do an inventory top-down, but we can do a budget for you, okay? We can balance the checkbook. So if we have a satellite or we have a bunch of ground-based measurements that are measuring air and measuring the amount of CO2 or methane in that air, we might make one measurement over one part of the domain. You might notice when you've gone to another part of the domain that the amount has changed, and go to yet another part of the domain, the amount has changed again. You might know that there was a wind blowing across the domain in that direction, and you might infer, well, gosh, there's got to be a way I can figure out how to get from these measurements I'm actually making and that wind speed. And there is. There's something called atmospheric inverse models, and that's the topic of the main meeting that's going on here all day today. The folks who actually make those inverse models are here to talk about their performance and how to make it better. And so what you do with these is you actually come up with the best fit you can to the fluxes in and out of the atmosphere needed spatially across your domain to produce the observed levels and concentrations of CO2 or methane in your atmosphere, okay? That's called a top-down method. Anytime you're using an atmospheric measurement of a trace gas in order to infer what the fluxes are, that's a top-down measurement, okay? Now, so we're making better and better atmospheric measurements as time goes on. We have a larger and larger number of sites. This is the Mauna Loa Observatory. That's one up in Finland. This is Wisconsin, basically a television tower that has a bunch of CO2 sensors running up and down it and methane sensors. We can do flux towers. We can put instruments on buoys. We have them on commercial aircraft in some places. Also research aircraft. We can have balloon flights. Those of you who know about Air Corps, we've flown a few from your parking lot over here. That was fun. We basically can get a lot of measurements from the ground. We also have up-looking spectrometers that can look through the whole column and get a column measurement as well. We also have a series of satellites. We have GOSAT, we have OCO. These make GOSAT makes measurements of methane and CO2. OCO makes measurements of CO2 only. GOSAT-2, methane and CO2. We have the second OCO instrument, OCO-3, is on International Space Station. And then we have TROPOMI over there making measurements of methane. So we have an increasing number of satellites in orbit making measurements of some quantity related to the total concentration of CO2. It's actually the column average dry air mole fraction of either CO2 or methane, okay? So we have a series of satellites that can do that. Okay, how do you actually make a measurement of CO2 or methane from space? We don't actually measure CO2 or methane from space. What we measure is reflected sunlight. You can measure thermal emission too, but thermal emission is just not going to give you any sensitivity to the near surface region because the emitting surface is at the same temperature as the air right above it, and so the air right above it emits just as well as it absorbs, and so you get no real information from thermal radiation. So we use reflected solar radiation. Sun comes down through the atmosphere, bounces back up to the satellite. It runs into a few oxygen and CO2 molecules and methane molecules on the way. And so what we then do is use that information in something called an atmospheric inverse or atmospheric retrieval model. That model includes a radiative transfer model that simulates the spectrum measured by the spacecraft. It has an instrument performance model, which has like the spectral resolving power of the instrument. It then has an inverse model, which basically is a nonlinear least squares constrained nonlinear least squares model that basically then can update your estimate for the carbon dioxide abundance in the atmosphere or the methane abundance to give you a better fit to the observed spectrum. And you just go around and around in a loop until that converges. You'll see more of that in a minute. Then, because we've made a measurement with a remote sensing technique, and that measurement is relatively indirect, The next thing we have to do is validate that measurement against every kind of measurement we can get our hands on. So this includes ground-based measurements, both direct in situ measurements, tower measurements, measurements from up-looking Fourier transform spectrometers, and balloons. And so we combine all of that data to validate our measurements. And then we put that into an atmospheric inverse model, and I'll just say, talk to everybody else in this room who's in part of the Transcom group to learn about how these things work. But basically, as I said, an atmospheric inverse model basically uses a transport model and an inverse model to estimate the flux distribution needed to produce the observed concentrations in the presence of the ambient winds. Okay, so I'm going to give you my 1.5 minute long atmospheric radiative transfer remote sensing theory class. So get your pencils out and learn all of this. An atmospheric remote sensing retrieval model includes a forward model, an instrument model, and an inverse model. We basically put a bunch of information in that might include things like atmospheric cross-sections for gas absorption, aerosol optical properties, the solar spectrum. We put information in about the pointing geometry of the spacecraft. We then, with that model, can generate a high-resolution spectrum, a perfectly resolved spectrum of the radiation that the spacecraft should have seen if it had a perfect instrument. But then we put in the instrument's actual performance characteristics, and we can generate a spectrum that then can be compared directly to the spectrum that was taken by the spacecraft. See how that works? Now, the inverse model is actually a constrained least squares model. So we're actually doing a least squares fit of our function, which is that thing there, and its Jacobians, which are the first derivative of them with respect to, it's like an adjoint for those of you who understand that language better. So we use, basically it's the first derivative of the radiances with respect to a change in CO2 or oxygen or water vapor or anything else that you're looking for, okay? So we use that information in order to update, the inverse model uses that information in order to update the state vector that we put in, which might be in a given concentration of CO2 or a temperature gradient or an aerosol distribution. And it goes around and around a few times until it converges and actually generates something that's a final atmosphere that produces a good fit to the data. And that's how we actually get an estimate of the column average CO2 or methane mixing ratio. Any questions? Okay. For a lot of you, some of this is really old hat, but I know that for a lot of you, this looks like black magic, and that can't, nothing's supposed to look like that if you're a scientist. So we make a few measurements with our spacecraft. The biggest advantage of the spacecraft is where this ground-based network has 200 stations, we make 85,000 measurements a day with OCO2 and another 85,000 measurements a day that are cloud-free with OCO3. We make about 1 million measurements a day from both spacecraft, but only about 85,000 of them are sufficiently cloud-free that I can see all the way down to the surface. And if I can't see all the way down to the surface, I can't see CO2 down to the surface. OCO3 is on space station. That was my flight spare instrument. I think it wants me to click or something. I dropped the first OCO in the ocean. Don't do that. It really makes for a terrible day. We spent 1,000 work years building it. We put it on a rocket, brought it to the launch pad, launched it, 3 minutes, 53 seconds, everything is perfect. Then the fairing didn't open. And with the extra weight, we made it to our launch altitude, going 6 kilometers per second. Does anybody know what the orbital velocity is for this planet? 7 kilometers per second. Yeah, so the repurposed ICBM remembered that it was an ICBM, and that mission lasted 10 minutes, and we had to build it again. That's OCO2. And when I built it again, the US Congress accidentally gave me $50 million I didn't ask for. I won't go through that story. But the head of the NASA Earth Science Directorate, Mike Freilich at the time, and I came to the decision that I would make a flight spare just in case I dropped another instrument in the ocean. Okay, we do the same thing for methane. Our colleagues on GOSAT mission make measurements of methane over the entire Earth. They're the best space-based measurements we currently have for methane in terms of accuracy right now. But the TROPOME instrument makes measurements as well and actually has much, much better coverage. It covers the entire Earth every day, essentially wall to wall, barring clouds. And so we get much better spatially resolved maps from TROPOME, but we get slightly better accuracy through GOSAT. So these measurements are now being used to study everything for TROPOME. For example, we can look at the US and we can see all of the wetlands that we know about, like the Mississippi River. You see the Central Valley of California. You see the oil extraction areas where methane's being emitted very nicely through the leaks and so forth. And then another thing that they've been doing is calling in high-resolution spacecraft to take observations to tell them where the leak actually is. We have very high-resolution systems that don't cover the whole Earth, don't have the sensitivity to see the anthropogenic emissions, for example, but they can see very large leaks, okay? That's another So, okay, I'm going to dash through this a little bit. I want to make sure I stay on schedule. So we have the ground-based network, and we haven't given up on it. This is, in fact, our reference for accuracy. Everything we do is absolutely critically dependent on our ability to use the ground-based and airborne facilities that we have, and we need a lot more of them. See the coverage we get? See where it's all concentrated? See where it's not concentrated. Some of you actually know that one of the biggest emitters of carbon dioxide on the planet is this country up here called China. How many stations? Then there's Russia, which has an incredibly active biosphere across all of Siberia. How many stations? The ocean. Those are ships of opportunity. Okay? We know that South America and Africa are amazingly active centers of action for CO2 and methane. Where are the stations? Our friends at NOAA are trying desperately to get better measurements in those domains. And they're doing aircraft experiments. They're heroic people going into domains that I would not venture into myself to make very accurate measurements and getting them out. So I thank you much for those of you doing that. Critical. But what we complement that with space-based measurements is a lot more resolution and coverage. And the resolution and coverage corrected to the measurements that we're taking with the ground-based measurements are actually giving us some really wonderful information about fluxes in and out of countries, for example. So this field is moving very quickly. We knew literally nothing at this level 10 years ago, and we're making giant strides forward. Those strides forwards are basically critically dependent on our ability to validate the measurements, and so what we're using to do that are uplooking Fourier transform spectrometers that are about 20 times as sensitive as our space-based sensors that make really, really accurate measurements, and we compare the space-based sensors to these, and then we fly aircraft over these to make detailed measurements of the column as high as we can get, up to maybe 25 kilometers with Air Corps systems. And Bianca's sitting back here. She's the one who flies those things. And so we get really much better information about the total column of CO2 in the atmosphere and also methane, and we can compare that to our space-based measurements and make improved results. We also have smaller devices. That everything on the right is an EM27 Sun. It's a small, almost portable, I say, if you have a strong back and a couple of people, you can move them around. That one's in, I think, somewhere in Central Africa. But we make measurements of CO2 and methane from the ground, from those systems. Also, we have Air Corps. This is just, does everybody in the room know what an Air Corps is? Gosh, you've got to, right? A few people. It's basically a long, skinny tube. You basically seal off one end of it. You bring it up on a weather balloon. As it goes up, the air in the tube goes out, or the gas in the tube goes out. Then you cut the cord, the thing falls on parachute, and as it falls down, the air comes back into the tube, preserving its vertical profile. Okay? Gives us, and then you run out and get it, the fun part, put it against your analyzer, and read out the record of the profile that you've just taken. And believe it or not, this works incredibly well. And these things go to 25 kilometers altitude regularly, so they really get the whole atmosphere for us, or most of it. Now, so space-based measurements. I say a lot more coverage. Well, that's a day. That's not so great, is it? When we finally get a week, we get a few more soundings. A month, we're beginning to fill things in. That's a year. And what you're seeing in this, these are CO2 anomalies. What I've done is for every one of those tracks, we've just run a little median filter along it. And by doing that, you can actually go and look for things that are above or below average. The blue is below, yellow is above, and so what you can see is that all across the tropics here, which were supposed to be the lungs of the planet, taking up all of the CO2 we're emitting, not working quite the way we expected. Okay, so the data itself, just by averaging over a year, basically averaging out the effective winds, you can get maps like this that seem to indicate that China is emitting a lot of CO2. We can't quantify it using this because we don't know how strong the winds were. Central Africa seems to be emitting a lot of CO2. All the way across, this was 2015, guys. This was a great big El Nino year. And the tropics, this was the first thing we saw with OCO after we flew it, and it really scared us to death. We thought either we don't know anything about this system or it just changed. That's where we still are today. Okay, so once again, you can play games like that with just the data itself, and this is another year. That's 2016. See, it looks a lot the same. 2017, woo, that was a La Nina year. Look how much things changed, see? 2016, 2017. Pretty amazing, right? Big changes. This is just looking at the data, the raw data. But we all know that what happens when CO2 or methane is added to the atmosphere, it's ejected away by the winds. And if you really want to know what's going on and you want to make measurements that are really much more sensitive than those that take years to average together, you're going to have to actually take that into account explicitly. And that's what atmospheric inverse models are for. Atmospheric inverse models assimilate the CO2 data as well as other data. They use wind data as well, and then they can actually come up with, so that's the transport model, and then you have an inverse model. So you added the data and a prior in to constrain everything, and then it produces maps of fluxes. You'll see a little bit more about that in just a moment. So, okay. With this, what we've been doing is creating top-down maps. We've been assimilating both the space-based data and ground-based data into these models. We can then make estimates of what we actually measure is the total net carbon exchange, this guy over here. That's the guy that we actually make a measurement of. We measure everything that comes in, the net of everything that comes in and goes out, right? What we want to know typically is the net biospheric exchange. We already sort of think we know the fossil fuels pretty well. Okay, so what we found is that we can't really discriminate with the current generation of models and data. We can't discriminate the anthropogenic sources and the fossil fuel sources, I should say, and the land biosphere separately. But if we can just assume we know the fossil fuel sources, and we have very good records of that, we can get a very good estimate for what's going on with land use change. Okay, and we can do that on any scale up down to about 1 by 1 degree. So we can also take that. That's a net biospheric exchange up there at the top. This is from the latest OCO2 MIP, a multi-model intercomparison experiment. We've been using multi-model intercomparisons because it turns out the transport models, we don't really trust any one of them. But together, they're giving us answers that look kind of reasonable. So we're beginning to trust the MIPS a little better. And individual models within the MIP, we're beginning to either trust less or trust more, depending on every data point we have and our ability to compare those two. We're combining those with other kinds of information. The plots on the right are actually not CO2 or methane at all. They're solar-induced chlorophyll fluorescence. When sun shines down on plants on land, the plants actually absorb a lot of that sunlight to do photosynthesis. But as a part of that process, they re-emit from 1 to 2% of the light, if they're healthy, as fluorescence at a longer wavelength. They actually shift it redward from where they take it. The blue light, they turn it to red light. Okay? You've probably seen a bunch of articles that have come out in the papers over the last few days about an article that just got published that talks about how we can use these measurements to actually assess flash drought. Because SIF is very sensitive. Nick over here is my expert on SIF. He can correct everything I'm saying, which is probably wrong. But this particular kind of measurement is being now combined with the inverse models to help us understand and attribute the actual source of CO2 fluxes that we're seeing. And that's another kind of data that we're using, putting everything together to try to understand how the system works. By the way, we kind of know where the sources and sinks are now. We didn't when I started this. If somebody asked me when I started the OCO mission back in about 2000 where the sources and sinks are, I would say, well, your main sink is in the tropics. Yeah, not so much. Just because there's so much biomass, there's just so much of the land carbon cycle, right? Whereas high northern latitudes, I've been to high, how many of you have been to Alaska, for example? The trees are everywhere, but they're this big. And the soil is that deep, at least the stuff that's not frozen year-round, at least in the old days. It's been a few years, right? So now the soil is not deep and it's unfrozen. So in any case, we're learning a lot about the natural carbon cycle and how it works with these measurements. There's no doubt about that. We're also making measurements of, we basically, over time, these are time series of the fluxes. And you can see they're really quite complicated because over the seasonal cycle, we have the land biosphere in particular. Sometimes it's, in the summers, it's taking up CO2. In winter, it's putting it out, and so forth and so on. And we can track that kind of information with our space-based and ground-based measurements. One of the things I wanted to point out here, though, is that these are all on the same scale. And the total is down there on the lower right. Upper right is the land fluxes from a model. This is Junji Liu's model. It's a CMS flux, it's called. It's actually a NASA model. That's anthropogenic emissions, basically basically in the wintertime, we burn more fossil fuels. Basically is what that's telling us. And mostly in the northern hemisphere, as you can tell. It's us. That's the ocean. The ocean's a major contributor to CO2 fluxes. But the fluxes, it's just big, and the fluxes are really small. So the perturbations in CO2 that they produce are small. And our data is not quite good enough yet. At least the space-based data is not good enough to quantify the fluxes from the ocean accurately. Ground-based data is good enough, but there's so little of it. Ships of opportunity, buoys, all of the autonomous vehicles we've got in the ocean are sampling 1% of the 1-by-1 grid boxes across the ocean basins every month. 1%. We need a slight expansion of that to make the measurements over the ocean, or we have to learn how to make space-based measurements that are actually useful over the ocean. Dave Baker's been helping us, trying to push us in that direction too. And I've been working as closely as I can. Okay, so this is just a flux map. It was put up here primarily to make that last point. The fluxes over land are much, much larger than the fluxes over the ocean. We're doing a pretty good job over land right now. I'm not saying it's perfect, but it's getting a whole lot better. And we're learning where the main sinks are, say across Northern Europe, across Northern Canada and East Coast and the US. That's corn in Iowa. We don't let corn grow in Iowa. We make corn grow in Iowa. We fertilize it, we water it, we push it as hard as we can, and it takes a lot of CO2 out of the atmosphere, okay? So that's what that's telling us. But look at the oceans again. You see this really subtle signal of flux here. That's all you get. So we have a critical gap in the ocean sink. The oceans are a critical part of the carbon cycle. They're basically taking up about 26% of our anthropogenic CO2. But the fluxes and the anomalies associated with that variations are so small we just can't see them from space right now. One of the kinds of questions we need to ask is, how is this going to change in the future? Is it likely to change? Let's say when the climate warms and the ocean circulation changes. Is it likely to change due to just Henry's law when if our policymakers ever wake up and decide to actually control CO2, when they bring CO2 toward net zero, could it be that the ocean sink might kind of start giving it back? Any ideas? Need to work on that. Okay, so, and we also need to measure it, because if we don't make measurements and be able to prove to our policymakers that we really understand what the hell is going on and that their policies are actually working, this is going to be a major impediment going forward, okay? And the other thing is we just really have to know how the ocean is going to help us in the future, is the bottom line, because right now it's a tremendous help, taking up 26% of our emissions. We desperately need better measurements over the ocean. Okay, so in addition to that kind of work, we've been making measurements over localized hotspots. This is the one called Los Angeles. It's a localized hotspot. We take measurements with things like OCO3, and we can measure CO2 emissions and their spatial distribution across the basin nowadays. Large coal-fired power plants. This is the Belkachow power plant. You can actually see a single power plant. You can see its emission plume. That's that red thing going down to the bottom there. And we can quantify that, and we can get within about 15 to 20% of what they can do with a stack monitor in the stack itself. So we can do a pretty good job for the very few power plants we can actually fly over. OCO flies over only 7% of the world every month. That 7% of the world, about 80% of that is cloudy. So we get about 1% a month, so we don't get a lot of power plants right now. But as time goes on, we're going to have better sensors that will make more measurements from space, and we'll get more of those. Sensors like Tropomi are actually making measurements over, that's a Texas oil field over there. That's basically the panhandle going up and the nose of Texas coming out over here to the right, Big Bend and so forth. But those are the Texas oil fields, and you can see methane coming out from them. And as I noted earlier, we're actually using high-resolution spacecraft to help us locate the actual sources of the leaks, and so that we can report them to the people who own the systems, with the hope that they'll go and fix the problem. That's dollars in the air to them. They've got every motivation for fixing these problems. So we have a whole host of different types of facility scale mappers. We found out that even our simple imagers like Landsat can measure these plumes. So what we do is we use sensors like Sentinel-5, precursor Tropomi. We say, there's some more CO2, more methane coming out over here. Could you go take a look? And so they go look through their data set, and either it's a global data set like Sentinel-2, or it's a more localized data set like Landsat. You have to go through a bunch of data to find these things. But people are doing it, and we're learning stuff about where the sources are. Okay? So now I'm going to shift gears. So we're feeling our oats. We're feeling like, boy, we really understand the system now, right? Not so much. In fact, we're still struggling mightily with the data that we have, both from space and from the ground, and with the models that we have to understand how the carbon cycle is working and how anthropogenic activities are modifying that carbon cycle. But don't think for a moment that's going to stop us from trying to help our policymakers make better decisions. So we're going to actually go and take the data that we're making here, and that's actually a map of emissions, net emissions from countries around the world, which was produced by the OCO MIP group led by Brendan Byrne for this. And the data basically shows, as we all know, the principal emitters of CO2 are China and the US. India is the next biggest country, but Europe together actually emits more than India does. We knew that from bottom-up inventories, but this is just reinforcing that. But it's also telling us about everything else in the system that's going with this. So it turns out being extremely useful because it's telling us about the natural biosphere, about land use policy, land use change policies as well. But that's not how nations stack up and compile their inventories to report them to things like the UNFCCC. That's not how they do it. What they do is they divide their energy or fossil fuel use into sectors, like energy, industry, agriculture, forestry, and other land use is what AFLU stands for. We also use land use and land use change and forestry, LULUCF, just to confuse everybody, right? I don't know why. In any case, and then waste. And what they do is they can put these things together and they count every barrel of oil, every ton of coal, every whatever, and they put them all together and they generate these bottom-up inventories that are increasingly detailed, especially across the developing world. But now you're Nigeria, and you've just signed the Paris Agreement saying that you're going to produce an inventory every 2 years like this. Your resources include 2 people in an office that's not very well equipped. They really didn't have the resources to do this, but they promised to do it, and we thought we could help. But the idea then is to put all those together into the global stocktake. That's part of the transparency framework, is putting together these inventories. That goes into the national implementation strategies and something called nationally determined contributions, where countries say, this is what we want to do to reduce our CO2 or methane emissions, or NO2 emissions, or N2O emissions. And then that goes into a global stocktake that's conducted every 5 years, just to see what our collective progress toward all of this is. So, can we help? Is kind of the answer, or the question Bottom-up inventories are great for tracking known sources with known activities and emission factors. They can yield direct insight into the effectiveness of emission strategies because you know what's producing the emissions. They can also provide the prior information we need for our atmospheric model. So they're absolutely critical, and I hope they get better over time. But the problem is, if you don't know about a source, it's not in your inventory. And even worse than that, a lot of sources you're not even required to report on, like unmanaged land. You're not required to report. Nobody reports on that. Nobody reports on the ocean, okay? So top-down inventories. These give us an integral constraint on the amount of CO2 and methane that's going into the atmosphere that's actually really, really good, okay? So this is a great way now, with greater and greater spatial resolution, we can help them understand their collective progress on regional or state levels to actually meeting their goals, okay? We can offer what I call a partially independent approach for looking at the completeness and accuracy of the inventories. We can track emission changes on unmanaged lands as well as managed lands. We can also look at other areas that really aren't being tracked very well, okay? And we can help them improve the traceability of emission policies to the thing that the actual climate cares about, which is how much CO2 and methane there is in the atmosphere, okay? That's what we're good for. Now, so we've generated some budgets. They're shown here. They're kind of budgets. Basically, we chop things into fossil fuels, rivers, runoff, and so forth, because the individual bottom-up inventories take that into account. We look at the delta carbon in the land biosphere, for example. We then look at the fossil fuels is that red thing up there for the US. You see where that bar is? That's the biggest thing. But notice that land use change in the US is actually countering the fossil fuel emissions, basically reducing it substantially. Some parts of the world, as we get into the tropics, not so much. The tropics are claiming sinks that they don't really have, is what we're seeing. They think that they're a CO2 sink, they're a CO2 source, the land biosphere in particular. But they have relatively small fossil fuel emissions there. So we're still the problem. Places like Australia, it's right on the zero line. It's like their net emissions are zip, hard to measure. So, and we did that for methane as well. John Warden did the methane. As I said, Brendan Byrne did led the CO2 effort using basically NASA Carbon Management System and OCO and GOSAT data, the best data we had available. So the idea is, once again, bottom-up inventories are source-specific they give you source-specific estimates of emissions from known sources with known emission factors. But they can miss stuff, especially over the land biosphere. Good for fossil fuels, not for land biosphere. Top down, we provide an integral constraint on the system, and we can track emissions changes even in places that nobody else is looking, okay? So in principle, it'd be great if we could combine these two, and this is what we tried to get everybody to do. This would increase the transparency. The top-down stuff is all completely transparent. The bottom-up stuff, not so much, as you might imagine, okay? We can compare them to actually also understand collective progress and understand what we need to correct and make better in the future. In practice, this is really complicated and hard to do, and we walked into the first global stocktake thinking people would pay attention to us. We brought our products in and we put them on the table, and they were ignored. Why? Because there was no mandate that anybody had to use them. But there was a mandate that they turn in some numbers. So they turned in numbers. Not everybody turned in numbers. Actually, only a small fraction of all nations who promised to turn in numbers actually were able to do so. But they wouldn't even take our numbers because they weren't compiled according to the rules, okay? So we're trying to do better in the future as we go forward. So lessons learned, they weren't widely used. And one of the reasons is they don't understand what we're telling them. They don't understand what the products are. They don't understand what box they put that in their bottom-up inventory. They don't really distinguish policy-relevant things. Transportation sector or energy sector. I can only put a law that, it can't say has to do both, right? You got to kind of tell people what they're going to do, right? There are lingering concerns about the accuracy of our data. We're working on that. And the other thing was there just wasn't enough time. Everybody ran out of time. That's really the bottom line. If you go to the inventory compilers, they say, God, thanks for that. That's a really great contribution you made. I didn't even have time to look at it. Maybe next time. Okay, so that's on us. So addressing these issues, we need to do some capacity building. We need to teach people about what these products are, what they aren't, what they can do, what they can't do. Okay? And we're going to do the best we can over the next few years doing that. The third obstacle up there is we're working on that every way we can with better measurements, with better models, better validation, everything else we can do. But inevitably, we have to traverse this last mile to support the second global stocktake. The thing is not all lost, though, because when it comes down to it, even though our stuff wasn't used very much in the first global stocktake, they're now actually being used to help try to understand what the collective progress is across the whole globe and also across regions like the tropics, regions like mid-latitudes, regions like the global south, for example. They're also being used to tell us what the natural carbon cycle is doing. They also provided a critical baseline that can be used in future stocktakes to see whether we're making any progress. So all was not lost. We established a baseline. We showed up to the party. We did what we said we would do as the systematic observation community. We provided products that can help them to manage carbon emissions over time once they actually start doing that. We're the bad guys in the room almost always because we're showing them that they're not doing anything yet. That CO2 curve is still going up. The methane curve is actually accelerating. And so is the CO2 curve. We haven't ever seen as much CO2 go into the atmosphere in a year as we did last year. It's just crazy stuff. But a lot of things have happened that are good. The World Meteorological Organization is now saying we want to generate an operational product like the ones you guys delivered to the UNFCCC. That didn't happen before we delivered our product to the UNFCCC. We have the United Nations Environmental Program just started an organization called the International Methane Emissions Observatory, which is looking for those large sources of methane emissions because they work with the oil companies and so forth, and they don't get the message out for us. We just make the measurement and they get the message out. We have 155 nations that signed a global methane pledge to reduce anthropogenic methane emissions by at least 30% by 2020, from 2020 levels by 2030. That's a really big step if they can do it. But given that actually those large leaks they're tracking are a tiny, tiny fraction of the total emissions, they really need to dig a lot deeper than that and understand what's anthropogenic and what's natural, how much is animal husbandry versus how much is waste, and so forth and so on. We need to get all of those things under control as well. We've got some new tools coming online. We've got some new spacecraft flying. MethaneSat just flew. It's up there. It's doing its in-orbit checkout right now. We might hear something from our friends down by Center Green at Ball Aerospace about first light while we're standing in this meeting. Who knows? Okay? It could happen any day now. We have a number of non-governmental players that are something we call new space. These are commercial vendors. They're places like the Environmental Defense Fund that flies MethaneSat who are getting involved in making measurements for us. And we're trying to get other people involved in making measurements, not just in space. We're actually focusing most of their attention on what we can do on the ground and in the air to try to get some new measurements for us. I'm spending a lot of my life doing that these days. So we've got some possibilities. We're making progress. We're not as far along as we wished we were before we brought our products from the science enterprise to the policy community in the commercial sector, but it is what it is. Do you think we could make perfect measurements or perfect predictions of weather when we started doing weather forecasting back in the 70s? Remember that? It was like, you basically hit persistence at 12 hours. And we thought, that's great, we're doing good. Then we got 2 days by 1980. When I was at GFDL, that was the thing. We got 48 hours, and then we hit persistence. Okay, look, the training wheels are still on with carbon tracking from the ground and from space and from top-down methods. But we were brave enough to put the damn things on. We maybe fell off the bike for Global Stocktake 1 in the sense that we showed up and mommy wasn't watching. But we'll do better next time. We'll make sure they're watching. And we'll make the biggest impact we can. As people that don't make policy, we make measurements. We report science. We understand how the system works. And we're going to do better in the future. But only by trying. Only by showing up. And we did that. So with that, I'd like to stop, take any questions. Thanks a lot.
Questions for Dave?
Oh, Lord. Yes.
Okay, so my question is about the ability of top-down approaches to inform the stocktake. I firmly believe that there is a role, but early in your presentation, you noted that some countries, especially developing nations, the inventories aren't very good.
Yes.
So could the uncertainties cancel out your statement, for example, that these countries claim large uptake, but really, it's very small? Or do we have a problem with the inventories that we're using for the top-down methods?
There's kind of several questions in there, but in the end, I think we have fairly high confidence right now that we can say that the natural biosphere across much of the tropics, a lot of the times, is more of a source than a sink. If you've got a number in there that you can date back to 25, 30 years ago that you have in there and you think that's the way it works based on somebody's measurement in a plot, you're probably more wrong than we are, okay, at this point. Things will get better over time too. So don't think that this is the end product. This is just where we are today. Okay? And I think as time goes on, our data is going to get much, much better. And we'll be able to make much more reliable. So at this point, I don't want to go head-to-head with an inventory compiler in Indonesia, let's say, saying what your country is doing is actually this. But I'll say, our data doesn't support your results, and maybe you need to go and look again. I'll say that. I think it's the best we can do right now. I mean, this is science, right? This isn't, nobody gave me something on stone tablets that I can walk into a room with. That's what everybody wants us to have. It doesn't happen. But yeah, I guess the bottom line is this is just the first step. It kind of gives you an illustration of what could be put down inevitably. We predicted the weather and it didn't rain in your neighborhood, you know. May be the case sometimes. That's going to be a part of it. Yes?
Does the absorption of the solar by CO2 depend on isotopes in a strong enough way to be able to get remote sensing of the isotopic signal that might help with the partitioning of fluxes?
Yes, in a sense, sunlight does include the signature isotopic isotopes. I can get C13 and C14 out of optical measurements. It turns out that I can't measure either one of those two from space with enough accuracy to not be laughed out of the room. Okay? So my error bar from space for C14 is like this big, and what we already know it about is about to this, and I want it to the thickness of a fingernail. Okay? That's the fact of light today. For C13, we're a little bit closer. From TCON stations, we can actually make a C13 measurement that is credible in that we can detect when the power plant boom blows over your station. But that's about where we are. But you know, as time goes on, things will get better. If somebody asked me to build an instrument that was focused on C13, I could build that instrument and it would do its job. It would give us better measurements. Anybody have $250 million lying? That's the issue there. But once again, from the ground, we can make very good measurements. We're making better and better measurements. We used to have to use accelerator mass spectrometry to do C14. People are learning how to do that with cavity ring down systems at this point. Now they're in the laboratory, they're fairly big, they're clunky, you have to bring the samples to them still, but they're a lot faster and you can get in line a lot faster than you can in your accelerator mass spectrometry measurements. So we're gonna get a lot more of those measurements as time goes on, I hope, if those projects are supported well enough, and I hope they are. Does that help? Okay, thank you. Yeah.
Are there any particular products that you feel like really stuck in the gold stock take aside from just nationally submitted inventories? Like, is there anything that seemed to be very appealing to the participants in the stock
We
take?
scared the hell out of it.
Okay.
The fact that we were coming in with non-national statistics that came not from a single nation, but from a global organization. What I didn't emphasize in this presentation, because of the audience, is that these measurements were brought to the UNFCCC by the Committee on Earth Observation Satellites, which is a group of 34 space agencies, everywhere. And we brought this information in and we said, here's what we see. And a lot of people didn't have any clue that we could do this. We could see over the back fence that they tried to keep up. We could see how well or badly they could do at a level that they were concerned about. Okay? And I presented this in Dubai. I want you to think about that. They let me out. But you can see how this goes, right? I mean, people didn't realize we could do this until we did it. So yes, that got their attention. The Earth Information Day is now a mandatory part of the global stock take, or of the COPs. So every COP, every year, we have something called Earth Information Day. We had 3 people sitting on the podium talking about this stuff, all morning long. The WMO stood up and said, we're doing this. It got everybody's attention, because everybody knows the WMO. It helped us, right? Because it was an int, not a country, right? Oh, back here, yes.
I know you gave a carbon talk, but can you measure N2O top down from space?
Barely. It turns out that our measurements, most of the action is right at the surface, and we're looking primarily at like fertilizer use and stuff like that. And it turns out that our most sensitive measurements for that right now only measure middle troposphere and above. So we can kind of get hemispheric averages, but almost nothing else. I can build you a near-infrared instrument that is focused on that problem. And I think we can do a lot better. But right now, nobody is focused on it. It turns out there's an absorption band at about 2.25 microns. It is weak and it's buried in a bunch of CO2, but there's no water around. So there's hope. It's just that we haven't done it yet, and I kind of ran out of money and time. So, next time. Yes.
Just probably know the answer to this, but to what extent is the top-down estimates being folded into the annual global carbon project?
Okay, up until last year, they weren't being used except as a, oh yeah, those guys. But starting in 2022, the Global Carbon Project started using top-down methods directly as a part of their analysis. So now they're folded in. The model I just showed, Junji's model, is actually the one that they used, is the main one they used this year in this year's accounting. So they're trying to do something that we're just beginning to get our arms around as a community, which is to reconcile not the national inventories so much, but the scientific inventories, which are kind of a different beast. I didn't get a chance to really talk about those. But they're integrating those guys together and trying to reconcile them and harmonize them so they have a better combined product. Once again, we need the bottom-up data just to know, because it's source specific, just to know where they came from. Just to know whether it was anthropogenic or natural or transportation or energy or waste or whatever it is, right? And then we need top down because it gives you the integral total. But learning how to put those together in a harmonious way and how to weight them because they give you different answers sometimes is just something that we're starting on. So that helps. Nick.
So you talked a lot about land and emissions. And we're doing a lot about emissions right now, and we're doing a little bit about land, but probably not enough. We're doing even less about oceans to understand what's happening now and how it will respond. So I'm wondering if you briefly mentioned it, that there is some work that there might be building a roadmap towards doing a better job tracking the ocean carbon cycle. Can you just talk about that a little bit?
I actually wrote a roadmap for ESA last month. Okay, so it's coming in. Their new decadal survey is coming in, and I'm unfortunately the guy who was in charge of the carbon cycle. That really has to scare, all of my carbon cycle colleagues should be scared to death when they hear that. And I wrote in a gap analysis on the ocean and a way to start trying to fill it. I think the kinds of instruments we're using today could do the job. They just have to be retuned. We have to use different exposure times. I need some small changes in the optimization of the instrument. I'm an instrument builder, so I look at everything from the photons coming in and what I can do with them. And yes, the information is there. But more than needing space-based instruments, which are absolutely critically needed, new space-based instruments, we can actually do a lot more with even OCO class data, and maybe even CO2M class data, okay, as it comes up. But to do that, I need a validation network that can tell me where the biases are. One of the biggest problems we're having with bias mitigation over the ocean right now is I don't know what the truth is. I don't have a truth metric that works, that's well enough distributed, that can tell me whether I'm getting better or worse doing this thing or that thing. So, somebody like Chris O'Dell could put together a great bias correction for us if I had anything to correct it to. So what we need before I even try to get spacecraft up there is a much better in situ setup for making measurements over at least critical parts of the ocean. We have almost nothing over the equatorial ocean right now. We need to make much better measurements there. We have a few measurements going on in the Southern Ocean because there's a lot of interest down there, and we're using that data, but it's a tiny little piece of the world. So, yeah, there's kind of a roadmap coming together. I'm trying to kind of, I'm spending somebody else's money, Europe now, not instead of the US. Our coffers have been hit hard enough. But once again, yeah, I think we know how to do that. And we just need to get the ground-based and airborne systems in place. And by the way, I say airborne. Any chance we can make air cores work over the ocean, like soon? I don't need anything going over maybe more than a few kilometers elevation, but I really, really need to understand what's going on in that first 2 kilometers. Because I've got to know whether the concentrations do this or do this, right? I don't know that now. I don't know how it changes over season, because I have nothing. So more commercial aircraft carrying our sensors will help us a lot because there are lots of places around, but there aren't a lot of places they land on water, so they're not going to give us very many profiles there. So I need new measurement systems deployed over the ocean to give me the data that I need to make the models work. So hope that helps. Yeah. There's a future here.
Better leave it there.
Yeah.
Can we all give Dave a big round of applause?
Thank you for letting me impose on your lunch.